Welcome to our program, Astronomy for Everyone. This month's episode marks a milestone in our program. This is our 25th episode, taking us into our third year on the air. We hope you've enjoyed all of the programs we've brought to you up to this point, and we look forward to doing it as well in the future. Our program for you this evening is on comets, and with me here in the studio is Steve Whitty. Steve, good to see you again.
Oh, thanks, Don.
Now, comets, what are they?
So comets are objects that orbit the sun. They typically have a big tail. You may have seen pictures of comets that have a big tail. So what generates the tail is that the comets have what we call volatiles. They're usually ices that in the vacuum of space, when the comet gets close to the sun, they turn from a solid, typically directly to a gas, and when they do that, they push out dust and other particles, little gravel bits, whatever, and this forms a sort of a cloud. And then solar pressure, the solar wind and so on, pushes this material away from the sun. So the comet has a tail that essentially faces away from the sun at all times through the orbit.
All right, very interesting. I think one of the most well-known comets out there is Halley's Comet. What have you got to tell us about that?
Yeah, Halley's Comet wasn't discovered by Halley. What Halley did was, it was kind of interesting. He was the first to study the historical record of comets. So this is around 1600, maybe 1650. He studied the historic record, which included comet sightings by the Chinese and the Arabs, and he saw that there seemed to be a bright comet that seemed to come back again and again, roughly every 76 years. And in addition, he plotted sort of a partial orbit of where he thought the comet was going around the sun for the very first time, and he suggested that Halley's Comet was in fact a periodic comet, that these weren't different comets that were being seen every 76 years, that it was in fact the same body, and he predicted its return. Now, he didn't live to see the return of Halley's Comet, so in his write-up he said, perhaps you could do me the honor of naming this comet after me if it in fact does come back.
And in fact it did.
And in fact it has come back numerous times, so we call it Comet Halley, technically. Now, we saw it in the 80s. I personally didn't see it because, not because I couldn't have, but because the comet hung around pretty much on the other side of the sun from Earth. It was a poor apparition. I mean, you could see it, but it was difficult to see, and I didn't get a chance to see it when it did. Now,
we've sent out a couple of different probes to take a look at Halley's. One was sent by the Russians and the other by Italy.
That's right. So the Russians had a series of probes called the Vega series, and these primarily were designed to go to Venus. And in fact, a Vega probe dropped an atmospheric descender, into a balloon, in fact, into the Venusian atmosphere, and then went on to visit Comet Halley. And it was the first spacecraft to arrive and get any kind of pictures at all, any kind of data at all, close-up data of the comet. A little bit later, and I'm talking, a few months later, the Italian spacecraft Giotto made a very close pass to Comet Halley, and this close pass got the best pictures of the comet's core, the nucleus of the comet. And now, having done that, it actually also took the most damage from the debris that was shed by the comet. So it took a real beating. Some instruments were lost, for example, but it got the best data.
Okay, and here we have this image up on the screen. What do we have here, Steve?
Yeah, this is the nucleus of of Comet Halley. So this isn't the whole, core. This is just the core. It doesn't have the whole coma. It doesn't show any of the tail really. And what you're seeing on the top there, the bright sections, those are jets of material that are coming off of the core of the comet.
The volatiles you talked about
The
earlier.
volatiles that I've talked about. So the whole comet, it's potato-shaped. It's not round. It's maybe 15 miles across, and so the object itself is fairly small. The reason why they're so bright in the sky and you see them is that the tail can stretch for millions of miles. And so you have millions of miles of material that can reflect light from the sun, and so they're quite visible.
Now we've had a number of other comets that we visited with space probes, Temple 1, for example.
That's right, Temple 1. So Temple 1 is kind of an interesting comet because we actually had a spacecraft not just fly by it, but actually drop an impactor into the comet.
And I think we have Temple 1 up here on the
We
screen.
have Temple 1 up here on the screen, and at the bottom of the screen, toward the bottom, there's a fairly prominent crater. It's not that big. It's not as huge as that one on the top, but toward the bottom you see a fairly prominent crater, and there's another crater right next to it that's harder to spot. And the impactor went between these two little craters at the bottom of the screen. And so the impactor was basically a big hunk of copper. Now it had its own spacecraft associated with it. So it had cameras. It was looking at the comet as it was impacting, and it guided itself to the comet. Anyway, the most of the mass of this impactor was made of copper because copper was not expected to be found in the comet itself.
So they could tell the difference between the material of the impactor and the material that was original to the comet.
Absolutely. And so the mother craft stayed away at a distance, and it took these images, and it got the evolution of the impact. The debris came up, etc. One of the sort of disappointing things that happened was that there was more dust and debris that was ejected from this crater, and so they couldn't actually see the crater itself. The size of the crater would tell them very much how strong the surface material of the comet is, and other interesting structural bits of.
They could tell whether it was more solid or just a loose ball of aggregate.
That's right, exactly. And but because there was all of this dust, they couldn't actually see the crater, and the mother craft whizzed by the comet before the dust settled. Data from actually X-ray data from the Swift Space Telescope showed that the plume lasted for 13 days, and it was at its most intense at about 5 days after the impact. So this event was actually quite significant. It took quite a while for it to sort of unfold. Up on the screen now is the impact position. So on the left we have an image from deep impact from the mothership. Just a zoom in of these two craters that were at the bottom of that other image. And on the right, we have re-imaging of the same location by another spacecraft about 5 or 6 years later. And the yellow arrows show the actual crater. And so we know, in fact, that the crater was about 150 meters in diameter. So you can think of it as 150 yards. And that tells us quite a bit about the structure of this comet.
Okay, what about another comet that was visited? We would say in English wild, but in German it's wild.
That's right. So it was named after the German astronomer who discovered it, and in German a W is pronounced like a V. So Wild 2, this was his second discovery, and Wild 2 was imaged up close by another spacecraft, the Stardust spacecraft. Now Stardust was launched, and it visited Wild 2 first, but it also had a sample return sort of a wand. It has this really weird material called aerogel, and it flew through the tail of Comet Wilt 2, and it returned a capsule to Earth with this cometary material in it. It also collected some dust, which is believed to be not of the solar system. So by returning this material to Earth, you get to use every instrument that has ever been, not just your best microscopes, but every instrument you can think of, and things that even haven't been invented yet. If you wait long enough, something will be invented, and you can study this material with it later. So the Stardust mission brought material home, and then it went on to. So in the image above, we actually see dust trails in this aerogel. The material enters the aerogel from the left in a little bit, and then as it moves to the right, it's expanding a bigger and bigger track in this material. So the material was then sliced into little slices and imaged with a microscope. The images were then, it was an awful lot of data to analyze and to even find these tracks. And so what they did was they enlisted the help of just anyone with an internet connection, and they put these images up on the internet, and you could sign up and you could say, okay, I'm on this image, and I've discovered, or I see something that looks suspiciously like a track. So you have a little bit of training, 5 or 10 minutes, and then you do this. And then multiple people got to look at the same image, and if multiple people see that, oh, there's a track there, then that's something that the scientists can then follow up with.
Now for Comet Hartley 2, this was also visited by Deep Impact as well?
Yeah, so Hartley 2 was, so once you put a spacecraft into, you launch it, you spent most of your money, because getting a spacecraft even into low Earth orbit is very, very expensive. But once it's out and wandering around the solar system, well, it's there, and why not use it as much as you can? So after Deep Impact went to Temple 1, they decided that they would go on and visit another comet as a continuing mission, the mothership.
Okay.
And so they actually had targeted a different comet. It's
was that Bothan?
Yeah, Botha, right.
Okay.
So they had proposed that they would retarget the comet to the spacecraft to visit Botha, but as they were approaching the Earth for a gravity assist to change the orbit of the spacecraft to make it to Botha, astronomers could no longer find Botha. It had become too dim, and what was assumed is that the comet had broken up and the pieces were too small to see. So what they decided to do was, at the last minute, right, was they decided to change the orbit to visit Hartley 2. And so for very little money, you get essentially 2 missions for one. You get Deep Impact to visit Temple 1, and then you get Hartley 2 as a bonus. And Hartley 2 was visited last fall. That's like November 2010, and it was great. It was a raging success. We got great images of this comet and great data from up close and personal.
Now, there's one other comet that I'm sure folks are very familiar with, back about 17 years ago, Comet Shoemaker-Levy 9.
Yeah, so in 1992, Gene Shoemaker and his wife Carolyn Shoemaker and one of their associates, David Levy, discovered a comet near Jupiter. So it was in a frame containing Jupiter. They were shooting on basically glass plates, shooting with I think it was a 40-inch telescope out by Palomar. And they saw this smudge, and they didn't really know what to make of it right away, because there was some question that the frame might have been damaged, exposed to light, and so they didn't know it was something that was exposed to light and it was a smudge for that reason or what. And so they asked a bigger observatory, I think it was with a 60-inch scope, to image it, and said, do we have a comet here? And they said, oh yeah, you've got a comet, but it's really, really strange. And it turned out that as this comet, Shoemaker-Levy 9, as it passed Jupiter, it broke apart, and it broke apart into a lot of pieces, over 20 pieces. And these pieces swung around in orbit, and 2 years later, in 1994, they crashed into Jupiter. And
I think we have the image of the string of pearls of Shoemaker-Levy 9.
So the Hubble Space Telescope took this awesome shot. So it looks like a whole series of comets, which sort of it is, right? And astronomers labeled them A, B, C, really imaginative names. They do this. A, B, C through like, I don't know, X or something, I forget. And I actually went down to, I was living in Philadelphia, and I went down to the Franklin Institute, and they've got a couple 20-inch, roughly 20-inch telescopes on their roof that they built in the 30s. And Jupiter's a very bright object, and so despite the light pollution in Philadelphia, you could still see these spots. And I got to see the G spot and one of the others, I forget. And they were huge. These scars on the cloud decks of Jupiter were many times the diameter of the Earth. They were just absolutely humongous, and they lasted for months.
I remember seeing some of those images from Hubble, and it was just fascinating to see them strung out across the cloud tops of Jupiter.
So, so we talked about how Comet Botha had broken up and had disappeared. Well, in 1994, we saw that not only do comets break up, but we also have comets that actually strike planets, and in our lifetime, right? So at the time, in 1994, one of the estimates was that comets strike Jupiter about every 500 years, and in fact, the Japanese discovered in their archives a hand drawing of Jupiter with spots that looked suspiciously like the spots that Shoemaker-Levy 9 left on Jupiter. So perhaps we were seeing something about 400 years ago. It would have been in the early days of the telescope.
This has been truly a fascinating conversation, Steve. I mean, we're all familiar with comets back in ancient times and even up to more modern times. Comets were seen as bringers of bad luck, a bad omen, but now we just know that basically they're just dirty snowballs. And we hope you've enjoyed this conversation, and we'll be back with more right after this. Welcome back. We're here again with Steve Whitty to talk a little bit more about comets. Steve, we've got some news about a comet, Anne Frank.
Right, Anne Frank is an asteroid.
Oh,
so we were talking about the Stardust mission,
Yes.
which visited Wilt 2, the comet Wilt 2, and then it had the second visit of Tempel 1. But before it even made it to Wilt 2, it had a flyby of asteroid Anne Frank. So asteroid Anne Frank is one of these fairly large rocks that orbits pretty much between Mars and Jupiter. So it's one of many asteroids that are known. It's one of only a handful of asteroids that have been visited up close. And the others are like Gaspra and Ida with its sort of moon, if you will. It has an even smaller asteroid Dactyl, which orbits it. That was a big surprise when that came out. So yeah, the Stardust mission got really 3 for 1.
Got a real bang for our buck on that one?
We got a lot of bang for our buck. I just wanted to mention that Stardust actually had a shield on it.
Okay.
And it was called the Whipple shield, and we'll talk about Whipple in a minute. So let's see what was next up.
Well, we were going to talk about Mr. Whipple and his book from the 80s.
That's right.
Yeah.
So right around 1994, when Shoemaker-Levy 9 slammed into Jupiter, and the bits of it slammed in alphabetical order, I was reading this book, The Mystery of Comets by Fred Whipple. And Fred was a researcher. He was an astronomer, and he didn't like set out on his career to learn about comets, but he was working for Harvard, and his boss basically said, we need somebody to study comets. And so for a great portion of his career, he studied comets, and he became the expert. He came up with the dirty snowball image. Anyway, I read his book, and when I got to chapter 9, I was absolutely astonished, because in chapter 9 he says, all comets break up. And what was astounding to me is that I'd never heard this before. And I had just witnessed Shoemaker-Levy 9 breaking up into, spectacularly. And Whipple basically said, well, they all break up. They get close to the sun, and the sun makes the volatiles, expand or explode, and the things break up. That's
gravitational pull.
That's right, absolutely. So that was amazing.
Sounds like a very interesting book, but it's out of print, right?
That's right. That's right.
Or maybe we can find it on the web somewhere.
Maybe on eBay or Amazon or something.
One never knows.
Yeah.
If you have any questions on any of the topics that we talk about, please send us an email. You can see our email address down at the bottom of your screen. We appreciate the ones that you have sent us. And of course, if you'd like any more information, please go to our website. That address is also at the bottom of your screen. And right after this, we'll be back with Term of the Month.
The term of the month for June 2011 is Asteroid. So what is an asteroid? So first, we're going to talk about what the word is. It comes from 2 sort of root words, aster, which means star-like, and oid, well, oid is sort of like, so it's star-like. And what they meant was that in early telescopes, and for the most part in any telescopes, asteroids are point-like objects. They don't resolve into a disk like planets do. So typically they're objects that orbit the sun, and they're not big enough to be planets, but also they're not comets. So they don't have a coma like comets do. They don't have a tail. There are an awful lot of asteroids that have been found in the solar system. There are over 535,000 registered comets with the Minor Planet Center. 251,651, as of yesterday, have orbits established that are good enough so that they can be given permanent numbers, catalog numbers. And there are over 16,000 asteroids that have names, like we had in Anne Frank earlier. The first of the asteroids was discovered, is named Ceres. It was discovered in 1801. And it has more recently been reclassified as a dwarf planet because it is really quite large. These asteroids, for the most part, they're not comets, but there is some crossover. The quadrantid meteor shower in January is thought to be caused by asteroid 2003 EH1, which we think used to be called C1490Y1, a comet that was discovered 500 years ago. The volatiles are gone. Term of the month for June 2011 is Asteroid.
Making the world a better place is an intricate puzzle. And piece by piece, the women and men of Rotary have worked hard to fight hunger, promote literacy, and move the world toward peace. But there is still much to be done, still some missing pieces. And one of those missing pieces is you. Learn how you can help Rotary put together a better world.
What's up in the night sky for June 2011? The month starts off, and I really mean starts off on the 1st with a new moon. Now normally you don't see the new moon, but in May I happen to see the very thin crescent moon just a day after new moon in the west as the sun set, and it was great. It was awesome. First quarter is on the 9th of June. The full moon is on the 15th of June, and the last quarter is on the 23rd of June. These are basically midweek weekdays. In the evening, for basically the whole month, Saturn is the big show. It's the king of the planets. In fact, it's pretty much the only planet that you normally see, that you easily see in June. But toward the end of June, Mercury starts being visible low in the west after sunset, starting maybe the 20th, and it gets better as time goes on. All of the other planets are morning planets: Mars, Jupiter, Venus, and they're all low near the sun, but as the month goes on, Jupiter gets higher in the sky. June 21st is the summer solstice. It's the first day of summer, but it's also pretty much the longest day. So sunrise is at almost 5 in the morning, and sunset is a little after 8 in the evening. So the nights are short, less than 9 hours. Back in the evening, in mid-June, if you look straight up, you'll pretty much see the constellation Boötes, and nearby it is the constellation Hercules. There's a glorious object, M13, in Hercules, and if you've got a telescope or even binoculars, it's a great tight cluster of stars. So that's what's up in the night sky for June 2011.